And we're going to start off basically going back to elementary school a little bit, describing solids, liquid, gases, but we'll go through it really quickly. So when we're describing a solid, how can we differentiate it from a liquid?
It's like you talked about, like physical appearances.
Yeah, how does it look physically different than a liquid? It's what?
It's together in one mass.
Yeah, it's together. So it retains a fixed shape and volume. Fixed shape and volume. The other interesting thing about this is the molecules making up a solid, or the atoms making up a solid, are actually moving. They're just vibrating. So the molecules vibrate. But do not flow. It's a little bit weird to think about molecules vibrating, but that is essentially what happens when a molecule gets warm or an item gets warmed. The molecules inside of it vibrate. All right? For liquids, they fill the bottom of the container. And they flow or move freely. So these vibrate even faster than a solid because they have the ability to flow. And then gases on the bottom fill the entire volume of a container. And they move really fast. There are other states of matter as well that our textbook doesn't really get into, one of which is called a plasma. Does anybody know what a plasma is? Not quite. Give you a hint. It keeps you warm. Fire, right? So if you think about what fire is, it's not really a solid, not a liquid, not really even a gas. It's a superheated gas, and that has its own unique properties. We're really not going to get into that. There's also gray areas between these that are pretty interesting. There's some situations where a mixture might behave both like a solid and a liquid. So if you think about a mudslide, for example, right? When a mudslide happens, it's solid land, but it's flowing like a liquid. So oftentimes those are called non-Newtonian liquids, meaning they don't behave exactly like a traditional liquid. So it's not black and white. Oftentimes there's shades of gray in between each of these. Make sense? All right. So let's take a look at phase changes. How many of you have ever heard about phase changes when you go from like a solid to a liquid or a liquid to a gas and whatnot? So some schools talk about it a lot, other schools don't. So we'll review it. There's a few phase changes I want you to know about. First one's pretty easy. It's melting. And most of you are familiar with it. That's where you go from a solid to a liquid. So if you take an ice cube out of your freezer, leave it on the counter, it will melt. Pretty easy to remember. Next one is a little bit harder. Vaporization. And does anybody know what phase change happens with vaporization? What state of matter are you going to, and what are you turning into? It's a liquid to a gas. So for example, if you boil water in a pot, you're turning it from liquid water into steam, which is a gas. And then there's condensation. Probably familiar with that on like your bathroom mirror, where the steam in the room condenses into a liquid on your mirror. So that's the reverse process, going from gas to a liquid. And then we also have freezing, which you're probably very familiar with. That's where you go from a liquid to a solid. And then there's also a unique one I wanted to share with you called sublimation. And this one's not always taught in high school, sometimes it is, but that's where you go from a solid to a gas. Does anybody know an example of some item that goes from a solid to a gas easily without going through a liquid? Dry ice, exactly. So if you've ever played with dry ice, it doesn't go through a liquid phase at normal room temperature. So let's make a note of that. The interesting thing with all of these is it depends on pressure. They depend on temperature and pressure, I should say. So a good example of that is if you've ever been camping at a high elevation or simply gone to a place like Denver, it actually requires less heat to boil water. And so you have to adjust your cooking times when you're at high elevation. It becomes a really big deal for people climbing places like Mount Everest. They essentially have to eat halfway cooked food because they can't get water hot enough to fully cook it. It's a kind of unique problem to experience at high elevations. Does that make sense? All right. So oftentimes what you'll see in chemistry textbooks is something that looks like this. This is a phase change diagram. And what essentially happens is, let's say you have something like ice down here. And ice, whoop, that's not how you spell ice. Holy cow. With ice, you can actually have ice go well below 0 degrees Celsius. You can have it cool to like negative 60 degrees Celsius, which is what happens in the Arctic regions. And you can slowly warm that up. It still is going to be ice until what temperature? 0. So for example, at 0 degrees Celsius, you go through this process where you melt that ice. And so for ice, this occurs at 0 degrees Celsius. And then once it's a liquid, you can warm that liquid up, but it still remains a liquid until what temperature? 100 degrees Celsius. Again, another reason why Celsius is way better than our weird system. And once you've got it as a gas, you can vaporize it. And then you can warm that gas up and get that gas as hot as you want it to go. So you do have these kind of plateau regions where you are undergoing a phase change. And if you go on into general chemistry, you'll talk about that in a bit more detail. We're not going to get into it much here, though. Does that make sense? Okay. The last thing I wanted to talk about today is something called intramolecular forces and intermolecular forces. So the first one we're going to talk about is intermolecular forces. And this occurs between 2 or more molecules. And the main thing to pay attention to is this has INTER, not RA, as the prefix. And it's the interaction. Actually, let me rephrase this. It's a non-covalent between 2 or more molecules. The way I like to describe this is it describes the stickiness of molecules. Some molecules tend to be really sticky. They cling on to one another tightly. Other ones really don't care about their neighboring molecules and just kind of ignore them to a fairly large extent. So the example I have here is a bunch of water molecules. And if you see, I've got a water molecule right here, I've got a second one right here, third, fourth, and fifth down here. And then these red dots connecting them are an intermolecular force where they're actually sticking to one another. Is anybody familiar with this intermolecular force? a hydrogen bond, which you may have heard of. And we'll talk about how to identify hydrogen bonds later, but hydrogen bonds are the stickiest intermolecular force. Does that make sense? All right. An intramolecular force is where you actually have something like a true covalent bond, where you have atoms that are stuck to one another, or a situation where you have a molecule sticking to itself, so kind of wrapping around and sticking to itself. All right, so let's really quickly describe why these are so important. Let me clean this up. And quite often I abbreviate this as IMF, just to make our lives easier. And the way I remember this is that stronger IMFs lead to a few physical property changes. Specifically, they lead to higher boiling points, and then higher freezing points. And the example I like to show is water, which we previously talked about, versus methane. Does anybody know where methane's found? It's found in natural gas, also found in decaying feces. So one of the biggest sources of global methane production is actually cows. I don't know if you're familiar with that, but it's a big problem. Cows produce a lot of methane. And the molecular weight of water is about 18 grams per mole. And the molecular weight for methane is pretty similar. It's about 16 grams per mole. So they don't weigh that much, or they weigh very similar masses. But if we look at the boiling point of water, we said the boiling point of water is approximately 100 degrees Celsius, although it does depend on pressure. And then the boiling point of methane at normal standard pressures is negative 165 degrees Celsius. So you can see, even though they have really similar molecular masses, the boiling point of water is over 200 degrees Celsius higher due to its intermolecular forces. Does that make sense? It's something that a lot of people don't appreciate is our planet is very unique in that we have water. Typically, all organic molecules that are small and lightweight like methane are gaseous, which means life is going to have a hard time evolving on those planets. Finding a planet with water is a really big deal because water remains as a liquid under a wide range of pressures and temperatures. Make sense? Yes. All right, so let's take a look at a few of the different types. I'm not sure if we'll get through all of them today. But we'll start out with the simplest intermolecular force called dispersion. However, people can't make up their minds with what to call this, so you may occasionally see this written as van der Waals. I think I'm spelling this right. Or you may see this as London dispersion. Or you may see this written as instantaneous dipole. Tomato, tomato, you can call it whatever you want as long as I'm clear with what you're talking about. All right, the really easy way to identify these is it's between two nonpolar molecules. Another way of remembering this is there's no net dipole. Does that make sense? However, when you look at something that doesn't have a permanent net dipole, you do have something called an instantaneous dipole, meaning electrons can't be everywhere at once. Electrons have to be somewhere. And so when that happens, you get this weird imbalance of electron density kind of shown here, right? So if you took a snapshot of this, at any point in time, you'd have some imbalance of electron density in one of your molecules. And then what can happen is this can match up with another molecule that also has an imbalance of electron density, and you get the stickiness between them. It's not very strong. It's relatively weak in the grand scheme of things. So let's make a short note. It is due to a momentary imbalance of electron density and it's thought of as weak. However, it really bugs me that textbooks always describe this as weak. So I'm going to show you the counterpoint to this little critter here. This is a gecko. And geckos are really fascinating little animals. I'm sure most of you have seen them, right? They can climb walls and even walk across ceilings if they want to. They actually are able to stick to the walls using London dispersion forces. So the weird thing that really matters with these forces is the surface area. So if you zoom in on this foot, you see all those little ridges on those pads. And if you zoom in even further, there's ridges on those ridges. And then there's little ridges in those ridges. So there's a ton of surface area here. And the whole idea is the molecules on the gecko's foot are nonpolar. If the wall's nonpolar, you get these weak interactions. But if they're too strong, you can't actually lift your foot off. So they've evolved to have the perfect balance in order to climb themselves up walls. The weird thing with this is there's actually government funding trying to figure out how to do this with gloves and things like that, especially if you're working in a field where maybe you're in the military and you need to go down a rope. You want to make sure that you don't slide down that rope too fast, right? So designing materials to mimic gecko feet is really a big field right now. So I did want to make a point. So geckos climb using dispersion forces. And then surface area increases the stickiness. I think it's a Y. Does that make sense? So maybe someday we'll have Spider-Man gloves. Yep.
So because it's momentary imbalance, is the force caused by that momentary imbalance occurring?
It just is more that, let's say you've got 1 billion molecules and maybe a handful of those have an imbalance of electron density and stick to one another. It's just those handful of molecules causing some change in physical properties.
But are they like moving or is that imbalance shifting?
Yeah, it's constantly shifting and changing. So it's kind of like if you took a snapshot at one set in time or one point in time, you'd see some of those molecules have an imbalance and are sticking to one another. That's really it.
And the molecules that have the imbalance are changing, so sometimes some molecules will have the imbalance.
Yeah, exactly.